In our vast cosmos of immeasurable proportions and limitless marvels, there's something profoundly poignant about what drives our greatest quest. The search for ourselves, for proof that we're not the only ones gazing up at the stars. A mere 40 light-years distant, nestled within the constellation Aquarius, burns a minuscule, faint star known as TRAPPIST-1e. Ancient, frigid, and nearly imperceptible to the naked eye, this unassuming stellar body harbors something truly remarkable. Not just one, but 7 planets comparable in size to Earth. It's almost as though the universe deliberately constructed an experimental laboratory. Can life flourish around such a diminutive star? Scientists have systematically eliminated most of these worlds from consideration as potential havens for life. Some prove too scorching, others too frozen. Many lack atmospheres entirely. The odds seem insurmountable. Yet one world continues to captivate our imagination, TRAPPIST-1e. Thanks to groundbreaking observations from the James Webb Space Telescope, we may finally be peering into its atmospheric composition. What these discoveries reveal is nothing short of extraordinary. Could this represent humanity's first encounter with a genuinely Earth-like world beyond our cosmic neighborhood? Might TRAPPIST-1e harbor life? I'm Alex McColgan, and you're watching Astrum. Come with me today as we voyage to the TRAPPIST, one stellar system to investigate the possibility for life on its most intriguing planet. We'll examine cutting-edge data from the James Webb Space Telescope that has stretched its capabilities to their absolute limits, unveiling the probable composition of TRAPPIST-1e's atmosphere and whether it can nurture life. That is, assuming the very star that grants the possibility of life hasn't simultaneously sealed its fate. TRAPPIST-1 belongs to the M8 classification of red dwarf stars, scarcely larger than Jupiter. It radiates a mere 1,800th of our sun's luminosity. Imagine comparing a solitary candle's glow to the blazing floodlights illuminating a university sports stadium. Though astronomers first identified this star in 1999, its complete planetary family remained hidden until 2017, when it achieved distinction as the first, and to this day, only, planetary system discovered by the TRAPPIST Optical Robotic Telescope Network. This sophisticated instrument comprises 2 components: TRAPPIST South, perched in Chile's mountainous terrain, and TRAPPIST North, stationed in Morocco's majestic Atlas Mountains. These telescopes employ transit photometry, a methodology that monitors rhythmic fluctuations in stellar brightness to identify orbiting planets. Put simply, when a planet crosses between our vantage point and its star, it blocks a fraction of the starlight, producing a measurable dip in the star's apparent luminosity. Through repeated observations, the telescope successfully distinguished the individual orbital patterns of multiple planets circling TRAPPIST-1. Initially, their data analysis revealed only the 3 innermost worlds. However, additional observations from both TRAPPIST facilities, combined with data from the Spitzer Infrared Space Telescope, brought the total to 7. Remarkably, all possess rocky compositions and approximate Earth's dimensions, making this the largest collection of Earth-like planets discovered around any single star. If you're interested in learning more about each individual planet orbiting TRAPPIST-1, I've created a dedicated video on the subject. You'll find it linked on your screen. But given the remarkably small and dim nature of the central star, is there legitimate hope that any of these worlds could sustain life? For these planets to receive sufficient stellar energy to support biological processes, their orbits must be considerably closer than Earth's distance from our Sun. Within the TRAPPIST-1 system, the planets certainly meet this criterion. All 7 orbit extraordinarily close to their host star. TRAPPIST-1e circles its Sun at merely 1/13 of Mercury's orbital distance, suggesting it may be tidally locked to its host star, meaning the same hemisphere perpetually faces a star, identical to how we only ever observe one face of our moon. This configuration carries profound implications for the planet's potential habitability, which we'll explore in greater detail momentarily. More encouragingly, this orbital radius places it squarely within predicted habitable zone, where it receives approximately 2/3 of the solar energy Earth receives from our Sun. This positioning explains why scientists find this particular world so captivating. Yet stellar radiation alone cannot sustain life. TRAPPIST-1e would almost certainly require an atmosphere, and that's precisely what scientists have been searching for using humanity's most sophisticated space-based observatory, the James Webb Space Telescope. The research teams instrumental in developing the James Webb Space Telescope were granted guaranteed observation time as recognition for their contributions. One consortium, formerly titled the Deep Reconnaissance of Exoplanet Atmospheres through Multi-Instrument Spectroscopy, aptly abbreviated as the DREAMS team, immediately prioritized observations of a TRAPPIST-1e system. The James Webb Space Telescope possesses unprecedented sensitivity and precision, so remarkable that it can identify spectral fingerprints within the razor-thin gaseous layers that constitute planetary atmospheres, even across a distance of 40 light-years. This achievement relies on a sophisticated technique called transmission spectroscopy. As an exoplanet transits across its parent star, James Webb not only quantifies the reduction in brightness, but also analyzes how the light spectrum transforms during this passage. The telescope's near-infrared spectrometer, abbreviated as NIR-SPEC, measures wavelengths of infrared radiation neighboring the visible spectrum. Molecular bonds absorb energy within this range, and different molecular structures, such as carbon-hydrogen bonds in methane or carbon-oxygen double bonds in carbon dioxide, absorb distinct wavelengths. Consequently, by determining which wavelengths are absorbed as a planet crosses its star, we can first establish whether an atmosphere exists and subsequently identify which gases comprise it. Obtaining clear readings from TRAPPIST-1 has proven particularly straightforward. In fact, our data quality surpasses observations of any other system by a factor of 10. Why this advantage? Paradoxically, it stems from the star's relative dimness. When a planet obscures light from such a faint star, it produces a proportionally larger decrease in apparent brightness compared to an identical planet passing before a massive, brilliant star. Greater contrast yield more precise measurements. Utilizing these measurements, the team has already definitively ruled out the presence of atmospheres around TRAPPIST-1c and TRAPPIST-1d. However, observations of TRAPPIST-1e, a rocky planet approximately 0.9 times Earth's diameter, yielded results so compelling that scientists couldn't dismiss them. Evidence suggested this world might genuinely possess an atmosphere. This tantalizing possibility provided more than sufficient justification for the DREAMS team to dedicate their entire allocation of guaranteed JWST observation time pursuing additional data. To date, they've observed 4 transits of TRAPPIST-1e using James Webb. What have these observations revealed? We can begin by eliminating several scenarios. Current evidence confirms that TRAPPIST-1e does not retain a primordial atmosphere, the kind planets are born with. These primordial atmospheres typically consist predominantly of lightweight gases, such as helium and hydrogen, neither of which has been detected. The star's intense radiation likely stripped these gases away during the system's early history. Similarly, it appears unlikely to possess a carbon dioxide-dominated atmosphere resembling Venus, which is exceptionally thick and dense. An atmosphere comparable to Mars, thin and tenuous, also seems improbable given the recent measurements. Surprisingly, all of these findings constitute encouraging news, as none of these atmospheric types would likely support life, at least not life as we understand it. So what kind of atmosphere might it have? Here's where things become truly exciting. There's a possibility of an Earth-like atmosphere, one dominated by heavier gases, such as nitrogen, coupled with substantial greenhouse effect produced by water vapor, carbon dioxide, or methane. Such an atmosphere, with surface pressure around 1 bar, equivalent to Earth's atmospheric pressure, might facilitate sufficient heat distribution to the planet's perpetually dark hemisphere, potentially sustaining a global surface ocean despite the tidal locking. Should the scenario be confirmed, it would generate headlines across the globe. However, that outcome might be overly optimistic. The data actually leans slightly toward suggesting that TRAPPIST-1e is a frigid world lacking a global ocean. Accurate data interpretation proves crucial here. Understanding what we're observing and its implications represents a distinction between the scientific discovery of the century and an embarrassing miscalculation. But if you're a scientist charged with data analysis responsibilities, don't worry. You can refine your analytical skills with Brilliant, the sponsor of today's video. Brilliant is an online educational platform serving both beginners and experienced learners. It hosts thousands of visual, interactive courses developed by an award-winning team of educators, researchers, and professionals from prestigious institutions, including Stanford, MIT, Caltech, Microsoft, Google, and more. Quite the impressive lineup indeed. I particularly appreciate their science courses, but they also cover programming, mathematics, and artificial intelligence, providing every tool necessary to evaluate promising exoplanets or tackle challenges close at home. You'll begin with foundational concepts, but will soon find yourself solving increasingly sophisticated problems as your skills and comprehension advance. To access Brilliant for free, click the link brilliant.org/astrum in the description below, or scan my QR code. My viewers receive 20% off premium subscriptions, so definitely explore this opportunity. It's an excellent way to support the channel. Now, let's return to TRAPPIST-1e. As I mentioned earlier, an alternative to an Earth-like atmosphere exists. Elevated methane concentrations can create a reverse greenhouse effect. TRAPPIST-1 maintains a surface temperature around 2,400 Kelvin, considerably cooler than our Sun's 5670 Kelvin, causing its energy output to shift toward near-infrared wavelengths. Atmospheric methane can intercept this energy before it reaches the planetary surface, then radiate it back into space, producing a cooler atmosphere overall. For the tidally locked TRAPPIST-1e, this will confine liquid water exclusively to the hemisphere permanently facing the star. No global ocean would exist here. However, this doesn't necessarily doom prospect for life. Such conditions could satisfy Darwin's famous warm little pond hypothesis regarding life's origins. Atmospheric modeling has corroborated this possibility. Simulations indicate that even if TRAPPIST-1e possesses limited water reserves, or if available water remains frozen on the planet's dark hemisphere, a stable atmosphere could still persist. Though this scenario might lead to what scientists term terminator habitability, where life could only establish itself within a dynamic band of perpetual twilight, separating eternal day from endless night. Surface water isn't the sole option, however. We know TRAPPIST-1e is rocky, but little beyond that. It might be an icy volcanic world harboring a subsurface ocean, similar to Europa and Enceladus within our own solar system. Some scientists believe Earth's earliest life emerged near deep-sea hydrothermal vents, and identical processes can unfold on TRAPPIST-1e. Regardless of where water might exist on TRAPPIST-1e, life remains possible. An energy source exists, along with potentially an atmosphere providing life's fundamental chemical building blocks. Yet one significant concern persists. Although all these scenarios remain possible, scientists cannot yet completely eliminate the possibility that TRAPPIST-1e is simply a cold, desolate, airless sphere devoid of any atmosphere whatsoever. Therefore, we must discuss what factors could prevent a stable atmosphere from ever developing. In this instance, the culprit is the red dwarf star TRAPPIST-1 itself. Imagine standing beside me on TRAPPIST-1e's surface for just a moment. Look upward. The star above would loom more than 4 times larger than our sun appears in Earth's sky. It would glow a deep crimson-orange hue, bathing the landscape in what resembles an eternal sunset. What a spectacular vision that would be. Red dwarfs are extraordinarily active, generating more powerful stellar flares than our sun, and with far greater frequency. The most severe geomagnetic storm ever recorded on Earth was a Carrington event of 1859, a greater than once per century occurrence. TRAPPIST-1 is believed to unleash flares of comparable intensity more than once every 2 days. You could potentially observe massive solar flares erupting into space in real time. These flares carry a tremendous amount of energy toward any orbiting planet, sufficient that over extended timescales, any atmosphere could be gradually stripped away, rendering life as we comprehend it virtually impossible. This assumes the atmosphere was permitted to form initially. Red dwarfs possess extraordinarily long lifespans. TRAPPIST-1 is projected to exist for 10 trillion additional years, 700 times the universe's current age. By comparison, our sun likely has only 5 billion years remaining before expanding into a red giant. You might assume that given a red dwarf's stability and longevity, abundant time would exist for life to emerge. However, because of their extended lifespans, their turbulent and energetic adolescent phases before red dwarf stars stabilize are proportionally longer. During these formative millennia, some planets begin generating their own atmospheres, gradually replacing their primordial hydrogen-helium atmospheres with compositions featuring heavier molecular gases, such as carbon dioxide, nitrogen, and methane. These chemicals emerge from within the planet through volcanic processes. The problem arises if the aggressive atmosphere-stripping phase of stellar development persists too long. An Earth-sized planet might exhaust its internal resources before fully establishing a stable, life-supporting secondary atmosphere. The sobering reality is that if a planet's atmosphere hasn't consolidated within approximately 5 billion years, it may never develop one, condemning the world to oblivion before life ever had a chance. I know, TRAPPIST-1e's prospects are sounding rather grim, and you're probably wondering, how is this considered one of the most promising candidates? But we don't yet know definitively whether an atmosphere has survived. We've already observed hints suggesting its existence. And although the star's violent outbursts could prove 1e's undoing, they might also be absolutely essential for initiating life. Ultraviolet radiation from stellar flares may be indispensable for synthesizing RNA building blocks, molecules fundamental to metabolism of every life form ever discovered. Now that TRAPPIST-1 has entered its calmer main sequence phase, with reduced UV and X-ray radiation compared to its turbulent youth, there exists a genuine possibility of a stable, habitable atmosphere persisting on TRAPPIST-1e. This atmosphere can maintain protection from ongoing flares through its own magnetic field, precisely as Earth does. Earth's magnetic field exists because its outer core consists of moving masses of molten iron and nickel. There's substantial reason to believe TRAPPIST-1e possesses a comparable system. In fact, TRAPPIST-1e's proximity to its red dwarf could actually help sustain its magnetic field. If TRAPPIST-1e follows an eccentric orbit, this would cause rhythmic compression and relaxation of the planet's structure. This process generates internal friction, potentially heating the interior by as much as 0.18 watts per square meter, approximately 24 times the tidal heating flux generated within Earth. We observe a similar phenomenon on Jupiter's moon Io. Io is tidally locked with an eccentric orbit, experiencing stretching and compression from gravitational interactions with Jupiter's other major moons, pumping it full of energy and making it the most volcanically active body in our entire solar system. So where does this leave us? We may have discovered an Earth-sized, volcanically active, rocky planet possessing life's essential building blocks, its own atmosphere and magnetic field, orbiting within the habitable zone of a relatively stable red dwarf. Or it could simply be a frozen, lifeless rock. Let us know in the comments which scenario you believe will ultimately be confirmed. We might not receive a definitive answer until proposed Habitable Worlds Observatory launches, a telescope specifically designed to search for life around stars similar to our own, scheduled for 2041. Until then, James Webb Space Telescope observations represent our best hope. The fact that we can measure light absorbed by a gossamer-thin gaseous envelope surrounding a rocky planet, orbiting a dim red dwarf star 40 light-years distant, is genuinely astonishing. And scientists haven't abandoned hope. They refined their approach based on initial James Webb data, modifying their techniques to achieve greater measurement precision. With 15 additional transit observations scheduled before December, they anticipate being able to confirm the presence or absence of carbon dioxide in the secondary atmosphere, a pivotal milestone in the search for life on TRAPPIST-1e. Perhaps TRAPPIST-1e and its neighboring worlds will prove to possess unique, inhospitable atmospheres, or perhaps conditions that could theoretically nurture life. Or maybe, just maybe, we'll discover something remarkably similar to home. It's thrilling to discover such significant potential for life in our relative cosmic neighborhood, even within such an extreme environment. But whatever TRAPPIST-1e's atmospheric composition ultimately reveals, combined with the recent discovery of geological formations on Mars believed impossible to form without biological activity, I find it increasingly difficult to escape the conviction that discovering extraterrestrial life feels inevitable. The only remaining question is, when? Then, in early 2026, something extraordinary happened. Dr. Sarah Chin sat in the James Webb Space Telescope Operations Center, her eyes fixed on the spectral data streaming across her monitor. It was 3:47 a.m., and she was analyzing the 12th transit observation of TRAPPIST-1e, one of the final scheduled passes before the mission team would compile their comprehensive atmospheric report. Her coffee had gone cold hours ago. The quiet hum of computer servers filled the room. This was supposed to be routine data verification, the kind of mundane task that occupied the gaps between groundbreaking discoveries. But then she saw it. A spectral signature at 7.66 micrometers. Sharp, unmistakable, and completely unexpected. Her heart began to race. She ran the analysis again. Then a third time. The signature remained persistent and clear. Phosphine. Not just trace amounts that could be explained by geological processes or atmospheric chemistry gone awry. The concentrations were significant, patterned, seasonal. On Earth, phosphine in a rocky planet's atmosphere has only one known source at these levels: biological activity. Dr. Chen reached for her phone with trembling hands. Within an hour, the DREAMS team had assembled via emergency video conference. Within 6 hours, 3 independent teams had verified the data. Within 12 hours, the discovery was confirmed by 4 separate analytical methods. TRAPPIST-1e wasn't just potentially habitable. Something was actively altering its atmosphere in ways that defied non-biological explanation. But that wasn't all. As the team dug deeper into the data, analyzing atmospheric layers with renewed intensity, they found something even more remarkable. The phosphine concentrations varied with the planet's rotation, higher on the day side, lower in the terminator zone, nearly absent on the night side. Whatever was producing this gas was responding to the presence of starlight. It was photosynthesizing. The implications crashed over the scientific community like a tidal wave. For the first time in human history, we had found not just the possibility of life, but compelling evidence of its actual existence beyond Earth. Not microbial fossils in ancient Martian rocks. Not ambiguous chemical signatures that could be explained away, but an active, thriving biosphere altering the atmosphere of another world in real time. Of course, questions immediately flooded in from every corner of the scientific establishment. What kind of life could survive in such extreme conditions? How did it originate on a world battered by constant stellar flares? What did these organisms look like? Did they huddle exclusively in the twilight zone, or had they somehow adapted to both the scorching day side and frozen night side? The phosphine signature told us that something was alive, but it couldn't tell us what that something was. We couldn't resolve individual features on the planet's surface. TRAPPIST-1e remained a pale, its secret still largely hidden. We knew there was life, but we couldn't see it, couldn't study it up close, couldn't understand the intricate details of how it functioned. Dr. Chen, now thrust into the international spotlight, addressed a packed auditorium at the Emergency International Astronomical Union Conference. "We stand at a threshold," she said, her voice steady despite the enormity of the moment. "For thousands of years, humanity has wondered if we are alone. Today, we have our answer. But this discovery opens more questions than it resolves. TRAPPIST-1e has shown us that life can emerge in places we never imagined. How common is this? How resilient is life in our universe?" She paused, letting her gaze sweep across the audience of scientists, journalists, and world leaders who had gathered for this historic announcement. What we found on TRAPPIST-1e isn't just another world. It's proof that life doesn't just survive. It persists, it adapts, it thrives against odds that would seem insurmountable. And if life exists there 40 light years away, orbiting a dim red dwarf under conditions we once thought impossible. She didn't need to finish the sentence. Everyone understood. The universe suddenly seemed far less empty. The discovery of life on TRAPPIST-1e ignited a transformation in space exploration. Funding for the Habitable World Observatory, once facing budget concerns and potential delays, was fast-tracked. Its launch date moved up to 2035. New missions were proposed to study red dwarf systems, which scientists had previously considered marginal candidates for hosting life. The philosophical implications rippled through human society. Religious leaders grappled with the theological questions. Philosophers debated the nature of consciousness and whether these distant organisms could be considered intelligent. Artists created works imagining the twilight world of TRAPPIST-1e, with its perpetual sunset and skies illuminated by crimson stellar flares. Children who had grown up believing Earth might be special, unique, the only cradle of life, now learned in school about their cosmic cousins orbiting a red dwarf in Aquarius. The Fermi paradox. The troubling question of why we hadn't encountered alien civilizations despite the vastness of space suddenly seemed less paradoxical. Perhaps we had been looking in the wrong places, expecting the wrong signs. Standing in that same operations center 18 months after the initial discovery, Dr. Chen prepared to initiate a transmission. It wasn't a message in any conventional sense. The organisms on TRAPPIST-1e were almost certainly not intelligent, not technological, possibly not even multicellular. The radio signals would take 40 years to reach their destination anyway, and another 40 to return if somehow, impossibly, anyone was listening. But it felt important nonetheless. Humanity's first intentional communication with another world harboring life. The transmission was simple. A mathematical sequence, the chemical formula for phosphine and the spectral signature we had detected. A message that said, essentially, we see you. You are not alone. Neither are we. As the signal departed Earth, traveling at the speed of light toward that small red star in Aquarius, Dr. Chen reflected on the journey that had brought them here. From a first tentative observation suggesting an atmosphere might exist, through the painstaking analysis of spectral data, to this moment, the confirmation that changed everything. The story of TRAPPIST-1e is far from over. It's merely beginning. Future telescopes will study the planet in greater detail, searching for additional biosignatures, mapping the distribution of photosynthetic organisms across its surface, perhaps even detecting seasonal changes as hypothetical TRAPPIST-1e years pass. We may discover whether life exists on the other 6 planets in the system. We may find that TRAPPIST-1 is not unique, that red dwarfs across the galaxy host their own biospheres, worlds teeming with life adapted to conditions radically different from Earth, and somewhere, perhaps on a more advanced world orbiting a different star entirely. Perhaps other beings are looking up at their own skies, conducting their own searches, wondering the same questions we've wondered for millennia. Are we alone? Thanks to TRAPPIST-1e, we now know the answer. And that answer has transformed not just our understanding of the universe, but our place within it. We are not alone. We never were. The universe is alive. And our search, our grand cosmic quest to understand our place among the stars, has only just begun. The discovery on TRAPPIST-1e proves that life finds a way, even in the harshest environments, even under the violent flares of an angry red dwarf, even on tidally locked worlds where day and night never change. If life can thrive there, where else might it be waiting, just beyond the reach of our telescopes, ready to reveal itself to a species finally advanced enough to look? The next chapter of human history isn't written in the stars above us. It's written in a light that reaches us from worlds 40 light-years away, carrying secrets encoded in spectral lines, whispering to us across the vast darkness. You are not alone. Welcome to the era of cosmic biology. Welcome to a universe that's finally showing us its true nature, not empty, not silent, but vibrant with possibility. And TRAPPIST-1e, that small rocky world orbiting a dim red star, has become more than just another planet in our catalogs. It has become a symbol of hope, a testament to life's tenacity, and a beacon guiding humanity toward our destiny among the stars. The search continues. But now, we search with the knowledge that somewhere out there, under alien skies, life looks back. 3 years after the phosphine discovery, Dr. Chen received a call that would shake the foundations of everything they thought they understood about TRAPPIST-1e. It was Dr. Marcus Webb from the European Southern Observatory, his voice trembling with an emotion Chen couldn't quite place. Excitement mixed with something that sounded almost like fear. Sarah, you need to see this. We've been running continuous monitoring of TRAPPIST-1e's phosphine signatures, tracking seasonal variations, building predictive models. He paused, and Chen heard him take a steadying breath. The phosphine concentration spiked dramatically. Over the course of just 6 weeks, atmospheric phosphine increased by 340%. That's not seasonal variation. That's not geological. That's... He trailed off. That's what, Marcus? Chun gripped her phone tighter. That's exponential biological growth. Sarah, something on that planet is reproducing at an unprecedented rate. And there's more. Chen was already pulling up her laptop, accessing the shared data servers. What kind of more? We're detecting other compounds now. Methyl chloride, dimethyl sulfide, nitrous oxide, all biosignature gases, all appearing simultaneously with a phosphine bloom. It's like the entire planetary biosphere just accelerated. Chen's screen filled with spectral data, and her breath caught. Marcus wasn't exaggerating. The atmospheric chemistry of TRAPPIST-1e had transformed before their eyes. Whatever lived on that world wasn't just surviving, it was thriving, expanding, changing its environment at a pace that defied every model they'd built. There's something else, Marcus continued, his voice dropping to nearly a whisper. The bloom pattern isn't random. It started in the terminator zone, and it's spreading. Deliberately, it's moving toward the night side. Chan felt a chill run down her spine, life spreading into uninhabitable territory. Or, Marcus said slowly, life making that territory habitable. Sarah, what if we're not just watching life exist on TRAPPIST-1e? What if we're watching it evolve? In real time? Within 48 hours, every major telescope on Earth and in orbit had been redirected toward TRAPPIST-1. The Habitable Worlds Observatory, still under construction, had its design modified to include advanced spectroscopic capabilities, specifically for monitoring the evolving situation. Emergency funding materialized from governments worldwide. This wasn't just scientific curiosity anymore. This was watching alien biology actively transform a planet 40 light years away. The press called it the awakening. Religious groups debated whether this was a sign of divine intervention or cosmic coincidence. Conspiracy theorists suggested the organisms were responding to our original transmission, though scientists quickly pointed out the timeline made that impossible. Not enough time had passed for our signal to reach TRAPPIST-1e and for any response to return. Dr. Chen found herself at the center of an international task force, coordinating observations from dozens of institutions. Sleep became a luxury she could rarely afford. The data streamed in constantly, each new measurement adding pieces to a puzzle that seemed to grow more complex by the day. "Look at this," said Dr. Yuki Tanaka, a biochemist who joined the team. She projected a 3D model of TRAPPIST-1e onto the main screen, color-coded to show phosphine concentrations. The expansion isn't uniform. It's following the temperature gradients, but it's also avoiding certain areas. See these gaps? Chen leaned forward, studying the pattern. The gaps formed shapes, geometric, almost structured. That looks intelligent. Yuki finished. I know, but it could be natural. Certain terrain features might be toxic to these organisms, creating natural barriers. Or there could be competing species, territorial boundaries. We're projecting human concepts onto alien biology. But what if we're not? Chen asked quietly. What if intelligence doesn't look like we expected? What if it's collective, distributed across an entire biosphere rather than concentrated in individual organisms? The room fell silent. That possibility, that TRAPPIST-1e might host not just life, but some form of planetary intelligence, was simultaneously thrilling and terrifying. Months passed. The bloom continued, but the rate of expansion had stabilized. The geometric gaps remained, and as higher resolution data came in, they revealed something that made even the most skeptical scientists pause. The gaps weren't random. They formed patterns, mathematical patterns. Dr. Chen stood before the International Astronomical Congress, presenting findings that would be remembered as one of humanity's most significant scientific moments. Behind her, a massive screen displayed the atmospheric map of TRAPPIST-1e's terminator region. Ladies and gentlemen, she began, her voice steady despite the gravity of what she was about to reveal. What you're seeing are phosphine-depleted zones on TRAPPIST-1e's surface. Initially, we theorized these were simply areas incompatible with the photosynthetic organisms producing the phosphine. However, further analysis has revealed something extraordinary. She clicked to the next slide. The gaps have been isolated, enhanced, and arranged in sequence. They form progression, prime numbers. 2, 3, 5, 7, 11, 13, 17, 19, 23, 29:31. The auditorium erupted in gasps and murmurs. We verified this pattern through multiple independent observations. The probability of this occurring naturally is... She paused, looking at the number on her notes. Approximately 1 in 847 billion. Either we're witnessing the most remarkable coincidence in the history of science, or TRAPPIST-1e's biosphere is deliberately creating a mathematical sequence visible from space. Dr. James Morrison, a famous astrobiology skeptic, stood up from the audience. You're suggesting that microorganisms, or at best simple photosynthetic life, are collectively arranging themselves to display prime numbers? That's absurd. Chin met his gaze calmly. 6 months ago, I would have agreed with you, Dr. Morrison, but we're not talking about individual microorganisms making conscious decisions. We're talking about emergent behavior, complexity arising from simple rules repeated across billions or trillions of organisms. Ant colonies build complex structures without any individual ant understanding the overall design. Slime molds solve mazes. Birds flock in intricate patterns. Why couldn't a planetary biosphere, given the right conditions and evolutionary pressure, develop planet-scale coordinated behavior? But prime numbers? Morrison pressed. That requires mathematical understanding, abstract thinking. Or, interrupted Dr. Tanaka, standing adjoining Chin at the podium, it requires survival. What if this pattern isn't communication in the way we understand it? What if it's a natural defense mechanism, a way of regulating population density, or a method of resource distribution that happens to produce mathematical patterns? We're assuming intention when we might simply be observing elegant biological programming. And yet, Chin added, we cannot ignore the possibility that this is intentional. That TRAPPIST-1e's biosphere has achieved something we never thought possible. Collective intelligence on a planetary scale, announcing its presence in the cosmos in the only language that's universal, mathematics. The debate that followed will continue for years, but one thing was clear. Humanity had to respond. Not everyone agreed on how. Some argued for caution, citing concerns about contamination, unknown risks, or the potential dangers of making contact with any form of intelligence, no matter how alien. Others pushed for immediate action, sending probes, attempting communication, accelerating our space exploration capabilities to eventually reach TRAPPIST-1e physically. Dr. Chin found herself in an emergency meeting at the United Nations, addressing delegates from every nation on Earth. We have 3 viable options, she explained. First, we continue passive observation, monitoring TRAPPIST-1e indefinitely without active engagement. Second, we transmit a deliberate mathematical response, acknowledging that we've seen their pattern. Third, we commit to a long-term mission, developing the technology to send a probe to TRAPPIST-1e within the next century. The delegate from China spoke first. Dr. Chun, if this biosphere is intelligent enough to create mathematical patterns, could be intelligent enough to pose a threat? A valid question, Chin acknowledged. But consider this, TRAPPIST-1e has been broadcasting its biosignatures for potentially millions of years. If any advanced civilization within range and concerns about this planet, they've had ample time to act. Moreover, we're talking about an organism or collection of organisms that took 3 years to expand across their terminator zone. Even if they possess hostile intent, a concept that may be meaningless to them, they're not exactly capable of interstellar travel. The delegate from India leaned forward. But Dr. Chun, you said it yourself, this biosphere is evolving rapidly. What it is today may not be what it becomes tomorrow. Are we prepared for the possibility that we're watching a civilization in its infancy, one that might develop far beyond our understanding? Chin was quiet for a moment, choosing her words carefully. Humanity has always faced unknown frontiers. We've always had to decide between the safety of ignorance and the risk of discovery. What makes us human isn't our ability to avoid all danger. It's our drive to understand, to reach out, to connect with something greater than ourselves. TRAPPIST-1e is offering us that chance. The question isn't whether there's risk. The question is whether we have the courage to accept that risk in pursuit of knowledge that could transform our understanding of life itself. The vote was nearly unanimous. Humanity would respond. Dr. Chen worked with mathematicians, linguists, and biologists to craft a message that transcended language, culture, and even the basic assumptions of human cognition. It would be pure mathematics, building from the prime number sequence that TRAPPIST-1e's biosphere had displayed, expanding into more complex theorems, then branching into physical constants, the speed of light, the gravitational constant, the fine structure constant. The message would essentially say, we see your mathematics. Here's ours. We understand you exist. We exist too. We are 40 light years away, looking at you across the vast darkness, and we are not afraid. On a clear night in March 2029, with millions watching around the world, the transmission was sent from the Arecibo-2 radio telescope in Puerto Rico, rebuilt after its predecessor's collapse. The signal would take 40 years to reach TRAPPIST-1e. If the biosphere responded, if it could respond, the return message wouldn't arrive until 2109. Dr. Chen, now 54 years old, knew she wouldn't live to see the response. Neither would most of the people involved in this historic moment. This was a message to the future, a gift to generations yet unborn. As the transmission completed, she stood beneath the stars, looking up toward Aquarius, toward a red dwarf star invisible to naked eye, toward a world where something lived and grew and perhaps even thought in ways humanity was only beginning to comprehend. "What do you think they are?" asked her colleague, Dr. Tanaka, standing beside her. "Really, in your gut, beyond all the scientific caution and careful language, what do you believe lives on that planet?" Chen was quiet for a long time before answering. "I think we're asking the wrong question. We keep trying to fit TRAPPIST-1e's biosphere into categories we understand. Intelligent or non-intelligent, conscious or unconscious, individual or collective. But maybe it's none of those things. Maybe it's something else entirely. Something we don't even have words for yet. Something that's neither animal nor plant nor fungus, neither machine nor organism, but something fundamentally new." She smiled, a mix of wonder and humility crossing her face. "I think what lives on TRAPPIST-1e is the future. Not our future necessarily, but a future. A path that life can take that we never imagined. And I think the most important thing we can do is remain open to the possibility that the universe is stranger, more diverse, and more magnificent than we ever dare to dream." The years that followed transformed humanity's relationship with the cosmos. The TRAPPIST-1e discovery sparked a golden age of astrobiology. Dozens of biosignatures were detected on planets orbiting other red dwarfs. Some showed the familiar signs of simple photosynthetic life. Others displayed anomalies that defied explanation, hints of complexity that might rival or exceed what had been found on TRAPPIST-1e. Dr. Chen continued her work, though she shifted focus to mentoring the next generation of scientists, the ones who might live to see the response from TRAPPIST-1e, if a response ever came. She gave lectures to packed auditoriums, always ending with the same thought. We stand at the dawn of a new era. For all of human history, we've been alone with our questions, our fears, our hopes. Now we know we're not alone. Something is out there under alien skies, living its own story. And someday, perhaps, our stories will intersect. Perhaps we'll learn from each other, grow together, explore this magnificent universe side by side. But even if we never make contact, even if TRAPPIST-1e's biosphere never responds to our message, we've already gained something invaluable. We've learned that life is not fragile, not rare, not confined to Earth-like worlds orbiting sun-like stars. Life is tenacious, diverse, and astonishingly creative. It finds ways to exist in places we thought were impossible. It evolves, adapts, and sometimes it surprises us with wonders we couldn't have imagined. So when you look up at the night sky, remember, you're not looking at an empty void. You're looking at a universe alive with possibility. And somewhere out there, perhaps something is looking back, wondering the same things we wonder, asking the same questions we ask. Are we alone? No, we never were. What comes next? That's the adventure. That's the story we're all writing together. Welcome to the cosmic community. Welcome home. And 40 light years away, on a world bathed in eternal red twilight, beneath skies crossed by stellar flares, in oceans or soil or atmospheric layers we couldn't yet imagine, Something grew, evolved, and persisted, waiting, perhaps, for the day when humanity's message would arrive, carrying greetings from a small blue world where other living things had looked up, seen the stars, and reached out across the darkness to say, "We see you. You are not alone." And that changes everything.